Alright, hi everyone. Okay, this video might not be based on AdMaths, but I'm choosing to upload this because one of my friends asked me to explain complex numbers to them, and I think that my explanation of why we need complex numbers in math might help a lot of other people. So this is a pure maths video. So if you're not doing pure maths, I recommend you to just click off. Alright, so have you ever wondered why complex numbers even exist? They might seem strange at first. Numbers, the imaginary part, but they're actually the natural step in the evolution of mathematics. Let's take a quick journey through the history of numbers to see how we got there. Okay? So it all started with like natural numbers like one, two, three, four. You can use this to like count apples. Or yeah. You can use this to like count anything because they're natural numbers. Humans use these to count objects, which is simple, right? But then we ran into a problem. What happens when you take away more than what you have? And by the way, natural numbers are represented by n, literally n. Okay, so yeah, then we ran into a problem. What happens when you take away more than what you have? We cannot represent zero using natural numbers. So they decided to introduce, sorry about that. They decided to introduce whole numbers, which are represented by, actually I'm not even sure. How are whole numbers represented? Yeah, as you can see, it was W. Actually, I knew it was W, but I wasn't sure. So whole numbers are represented by 0, 1, 2, 3. I noticed the main difference between natural numbers and whole numbers is that you can now represent 0. Okay, but even with whole numbers, we still can't describe things like depths or temperatures below 0. So they decided to introduce integers. So integers would be numbers like -1, -2, 0, 1, and 2, right? And the integer symbol would be a z, okay? And then, even though we have integers, we can't really represent division. Integers allowed us to represent loss, balance, and direction. But even with all those things, we still can't represent division. So they decided to introduce something called rational numbers. Rational numbers are numbers such as 1/2, 1/3, and the rational number symbol would be Q. That's the symbol for rational numbers. They were introduced to represent any number that can be written as one integer divided by another. But there were still gaps. For example, the diagonal of a square with side 1 is quarter, right? I mean, not quarter, square root 2. And this number cannot be written as a fraction, right? Numbers like root 2 and pi are irrational numbers. They fill in the infinite spaces between rationals, forming what we call the real numbers. Alright? So basically, real numbers can do a lot, but they can't do everything. Like, try solving this equation. No real number could work to solve this equation. You would get x equal square root minus 1. So how would we find a number whose square root is negative? This is where the idea of imaginary numbers come about. They say that I is equal to square root minus 1. Mathematicians define this symbol as imaginary numbers. Now we can express numbers in the form of x plus, no, it would be a plus bi, with I being the imaginary part and a being the real part. For example, 2 plus 3i. This is called a complex number. It consists of both a real and imaginary part. And surprisingly, this opened up entire fields of math, physics, and engineering because there are certain things that you just can't calculate, as seen with the example right here. You cannot find the value of x unless you use imaginary numbers. Okay? And now I'm gonna show you something quite interesting, so you can remember the powers of I. Right? Let's say you have a graph. This is a Cartesian equation Cartesian plane that we're all familiar with, that we should all be familiar with if we're at this level, right? So we have the y-axis, then we have the x-axis, all right? So it could be said that, oh, this is a complex plane, right? We can say that the horizontal axis represents real numbers, like 1, 2, 3. You get the gist. However, it is said that the vertical axis represents imaginary numbers like I and minus I, right? But here's the thing. Here's the thing that you can use to remember all the powers of I. If you rotate this, if you rotate 90 degrees, you actually get I. And I is equal to square root minus 1. But if you rotate it one more times, you actually are squaring the numbers. So you will get I squared. But what is I squared equal to? When you rotate it 90 degrees from I, you're at minus 1. So I squared is equal to minus 1. So how about we rotate it one more time? Let's rotate it again. As you can see, we're now at a minus I. So we can say that I to the power of 3 is equal to minus I. How about we rotate it one more time? Let's rotate it for a fourth time, actually. So we could say that I to the power of 4, let's check where it rotated to. It is at 1. So I to the power of 4 is equal to 1. How about we rotate it one more time? Right? This is our fifth rotation. I to the power of 5, what would that be equal to? I to the power of 5, it landed on I. So I to the power of 5 is equal to I. That means I to the power of 5 is equal to square root minus 1. Okay, so how about, I'm going to show you now how to actually plot these imaginary numbers on the x-axis. On the complex plane, or whatever it's called. Alright, so we have a graph right here. Okay? Of the real numbers on the x-axis, and then we have the imaginary numbers. Okay, so you would go to so let's say we're trying to plot a number like 2 plus 3i. So if you have 2 plus 3i, then you would actually go to 2 on the real axis, right? And then you would find where 3i would be on the y-axis. So you would just do this. Let me show you. Let's say this is 1, this is 2, and this is 3. You would go 2, and then you just go up to 3. So it would just be like this. You just draw a line from the origin, and boom, you just plotted a complex number. Let's do another one. Let's just do one more. Right, so this is y-axis, this is x-axis, right? Let's try to graph the complex number 2 minus 3i. So we have 1, 2, 3, minus 1, minus 2, minus 3. 1, 2, 3, 4, and minus 1, minus 2, minus 3. So we just go to 2 on the x-axis, which is right here. And then we would go to minus 3 on the y-axis. So then all you would do now is just draw a line from the center of, from the origin and bring it right here. That's all you would need to do to plot this complex number. So that would pretty much it. In summary, from simple counting numbers to complex numbers, math has always expanded to answer new questions. They didn't just introduce these new types of numbers for no reason. The existence of these numbers, the sole purpose of these numbers, is to solve equation. When a new equation pops up that cannot be solved with the numbers that we already have, it calls for a new type of number. That is how complex numbers came about. They aren't mysterious, they're just the next step in a long journey of problem solving. Alright. So I really hope this video helped you to like memorize the powers of I and really understand why complex numbers exist and how they look on a graph. Yeah.